Hi everyone, welcome to ATAR Notes Chemistry Lecture. I'm your lecturer today and my name is Mahima. So pretty much for this lecture, we're just going to be doing revision of chemistry. Before I do get started on the lecture, I'd just like to say a quick bit about ATAR Notes. We offer a bunch of different resources, some of which you already may be aware of. So obviously we have the lectures. We also have things such as like the discussion board, as well as like articles and like study notes that's already available on the forum. We also do have a brand new website that has been updated. So please do go check that out. And alongside that, we do also have further tailored resources. So for example, we have our TwoSmart program, which is pretty much like an online tutoring program. We also have Ed Unlimited, so that's pretty much like a place where you can get all your different study notes as well as the printed study guides if you guys do prefer that. And just a quick bit about me. So I graduated last year in 2021. I did 4U Maths, Bio, Chem, English Advanced, as well as French Continuous. And currently I'm studying biotechnology as well as law at UTS. And a fun bit about me is that I really do enjoy dancing and I love dogs, especially Labradors. So, before we do get started into the content, I would like you guys to hop onto Slido. I'm just gonna see, um, there's something wrong with my Slido, so I'm just gonna quickly go fix that right now. Because typically I should be able to, um, ask you guys questions, and it's not allowing me to do that for some reason. Do I just need to click present? Is it showing up now? There we go. So, how are you guys feeling for the HSC? Feel free to chuck in your responses. I know, it's very understandable, but nervous. Yeah. Excited. I think, honestly, I had a mishmash of like all these emotions. I was like scared because I didn't have that experience of trials, right? So for me, this was like a whole new experience. But I also was like, I'm just so ready to get over this at the same time. It's also very stressful, right? Because you're just not used to like sitting like, and it's also like, there's just so much, I guess, like thoughts from other people that just bog your mind as well. I felt that, especially from just like my friends. Anita's spoon coming up too fast. Yeah, I know. Time does go. Honestly, if I want to say my chemistry trial mark, I got 60% and I got a band 6 in chem. So if your internals are like really bad, you'll be just fine. So I'm speaking from my experience. I literally thought I was like, crap, I got a 60. I'm so screwed. But I turned out to be fine. So just focus on the externals because that's what is gonna matter. Like your mark's gonna count regardless of what you do in the externals. So yeah, I do see a range of emotions here. And I felt that as well. So I completely like understand. Um, so yeah, don't worry. It's okay. We all feel it at one point in time. All right, I'm gonna go ahead and stop the poll. Let's go back to our lecture. Alrighty. All right. So how this lecture is going to be structured is that there's going to be two content blocks. In the middle, we'll have a break and also opportunities for you guys to ask any questions. The first session or the first content block is pretty much just going to be like skills, general advice, as well as mod 5 and 6 questions. And after that, you can ask me any questions that you want to. All right. And if you do have anything just like popping up, let me know, and I'm more than happy to answer the question. All right, let's get started. And I've also tried my best to make sure that like you have like very detailed access. So if I'm not able to go through it, you can always just have access and read through it yourselves. But hopefully we should be able to get through everything. All right. The most important part of HSC really is your mental health. So make sure that you spend time not only studying but also just talking with your family and friends. Moving on to actually exam technique and answering questions, you want to make sure that you check the marks themselves because that's going to tell you how much you actually need to write. And also, like, the number of lines is also just an indication, but the marks also tell you like how much you need to write in terms of detail. So for like 1 mark questions, you can just write like dot points or like a sentence or an idea. For 2 to 3 marks, you can, try fleshing out your answer a bit. So use like a table, for example. And then when you start reaching like from 4 to, I don't know, 9 marks, which is the max that HSC questions could give you, you really need to start using paragraphs. And then once you're really reaching the 5 to 9 markers, you want to be subheading your responses. If you don't subhead, it could kind of get messy for your marker and they might not be able to understand, and as a result they might just deduct marks just because of that, and that's not a good way to lose marks at the end of the day. And yeah, for 9 markers, especially if it's like an assess or an evaluation questions, you want to kind of structure it like a mini essay. So you want to have like an introduction, your body paragraphs, and whatever you're like describing or analyzing, and then finally a conclusion that states what your assessment is within the final like few sentences. All right, so let's look at an example question. This question is asking the molar heat of combustion, and it's asking the energy generated per kilogram of CO2 released by combustion of ethanol. This question is a 3 marker, as you can see over here. And I know it's a calculation question, so it's relatively simple when you're talking about enthalpy, but you want to make sure that you realize it's asking per kilogram of CO2 rather than per kilogram of ethanol burnt. So whenever you're looking at questions, you want to make sure that you know exactly what you're calculating and not just go through the generic route. Moving on, calculation questions can also ask for sig figs. And my rule of thumb is that do sig figs in any calculation question, to the lowest number of sig figs, and then for pH, its lowest number of sig figs is the number of decimal places that you're using. But sometimes if you need to like kind of figure out if a question is like marking for sig figs, because not all questions in the HSC do that, then you want to be looking at questions that really have more marks than they're really worth, I guess. If they have like an extra mark for something that would typically be like 3 marker. And in this case, you can see that this question has 4 marks. And really all it's just asking is to calculate the equilibrium constant, which is relatively simple and should be really only worth 3 marks-ish. So from there, you would know that you need your sig figs, and your lowest number of sig figs in this question. All right, let's move on to a bit more about how you would, do exam techniques, or really what goes on in the exam. You need to focus on timing. Timing is really important in the HSC exam, and the only way that you can perfect your timing is just through practice papers. So it's really important that you try to pace yourself and kind of know what your weaknesses and strengths are in terms of MCQ and short answer. And also how you want to go through the exam. So do you want to start off with MCQ and then go to short response, or do you want to jumble that up a bit? Typically NESA recommends around 35 minutes. But if you aim around 40 minutes, that should be fine, because sometimes MCQ can get really hard. I found that a bit towards my 2021 HSC paper, if you guys have tried it. I felt that the questions that were towards the end were a bit hard, so I had to kind of spend some time on it, and then if I really was running out of time, I had to like just skip it, just guess something, and then just come back. So yeah. If you're struggling with MCQ, then just try doing a bit of trial papers and make sure that you're comfortable with it. In terms of ordering, which I was just talking about earlier, there are a few ways that you can do it. You can just do the regular kind of method where you have MCQ and then short answer. And in that way, you're not really missing anything, but also it's not really giving you any other disadvantages. It's just this normal structure. And that's what I prefer personally, because I felt like the MCQ questions at the start were a bit okay, so it kind of eased you into the paper, and then you would just encounter harder questions as you go. Sometimes you can also do your strengths to your weaknesses part. So I guess in this way, you're really like securing in your marks. But sometimes what might happen is that it just kind of could confuse you. You might be missing out on questions, or you might, think that you thought a question was hard, but then ultimately you could be able to do it. So I never really tried to do this method unless I found like a question really hard, and then I'll just skip it and come back later on. In terms of writing last, sometimes you might not give enough time to the long questions, so therefore you might not have time to actually plan and structure out your response in subhead, like I said earlier. So therefore, it could cause you to lose marks unnecessarily. So I don't really prefer this technique, but if this is what works for you, then obviously have a go at that. In terms of exam technique, completing it is like one thing. Checking is really important. Especially for me, like I make so many mistakes. And if I didn't check, I know I'd get a lot of questions wrong unnecessarily, right? And if you're in like the same situation, then I highly recommend you spend time checking. For me, I approximately spend at least 45 minutes to 1 hour checking. When I was doing practice, but ultimately when it came to the HSC, I was just kind of thrown off by the questions that they gave, because it's really hard to like predict what questions they could give, right? So I spent around approximately like probably 30 to 40 minutes checking. But either way, leave time to go through hard questions again if needed, and also check your calculations. I would always start off with checking my MCQ questions that I found were hard. So by doing that, you're making sure that you're less likely to make a mistake, and then check your calculation questions, as well as your equations, because I find that sometimes I might not have balanced it properly, and that will just ultimately affect my entire kind of structure of my questions. And then I also just like skim read my long response questions in case I just had something like a typo, or if there were like any silly errors. And like I don't know if they would like mark you down for like typos and stuff, but it's still good to have a nice and neat response anyways for your long answer questions. And then sometimes in my long answer I would just add like a equation if that would support my question. So that was pretty much how my exam technique in terms of checking looked like. Alrighty, in terms of study techniques, you really want to be studying in order to eliminate your weaknesses. At this stage, I don't think it's efficient to be just writing notes. If you're going to write notes, you're not really spending your time efficiently. If you want to work out your weaknesses, you could just do like a past paper, and then you would know what questions you're getting wrong continuously, and then review that kind of content. So you could review your notes for that specific sub point, and by doing that, you're really making sure that you're targeting on your weaknesses, and your strengths are not just going to disappear suddenly. So that's always fine. And I know it's kind of like, I guess, I don't know what the word is. It's kind of stressful to work on your weaknesses because it might make you feel down at the end of the day, but that's what's going to help you boost marks. And I think the best advice that I've been given during HSC was like focus on your weaknesses. And that's what I did as well. And as well, like I said, you need to practice, especially for like, oh my God, what happened here? All right, especially for like MCQ questions as well as calculation questions. You'll only really know how to do it once you practice it, right? And then you can also know where you're gonna make your silly mistakes. For me, it would just be like the simple like adding up things, or like putting something wrong into my calculator and things like that. So then in the HSC exam, you know that, okay, this is something I'd likely be making a mistake on, and then you can just eliminate it that way. All right, let's move on to Module 5 revision now. So today we're pretty much going to be covering Le Chatelier's principle, as well as equilibrium graphs, as well as calculating, so calculating KEQ, as well as KA and KSB, and KA is a bit of Mod 6 as well at the end of the day. I do have questions here and I've put in the solutions, but if you do have like any questions within the solutions themselves, just mention them like within the Slido section, and then I'll be happy to look back at it again. All right, let's talk about Le Chatelier's principle. So this is pretty much the principle that we use to explain a change in equilibrium. So when you have an equilibrium that is a dynamic equilibrium and it's being subjected to a disturbance, it will try to reestablish a new equilibrium to minimize the initial change. Don't use the word counteract, because like even if in LCP, like in an equilibrium, if there's a change, it's not going to completely go against it. It's going to try to minimize it. A change is still a change at the end of the day for the equilibrium. So don't use minimize. Don't use counteract, sorry. Use minimize. And this can really be used for a lot of different kinds of changes. So changes in temp, pressure, volume, if you're increasing or decreasing a concentration of a reagent as well. So yeah, make sure to mention LCP whenever you're given, like define LCP whenever you're given those kinds of questions. So let's consider this equilibrium. This equilibrium is between nitrogen dioxide and dinitrogen tetroxide, and you can see that delta H is negative, so therefore it is exothermic. We can also look at the molar gas ratio, so it is pretty much 2:1, and note that all of these are gases, so therefore pressure, volume can affect equilibrium, and so will concentration. If, let's say, we increase temperature, so therefore we have an exothermic equilibrium. If you want to increase temperature, it will try to favor the endothermic reaction that will absorb the heat. So therefore, in that case, the equilibrium will decide to shift left. If you're given a question that asks you to explain color changes, then you want to look at the colors of both of these species. In this case, nitrogen dioxide is brown, and then dinitrogen tetroxide is colorless. So if you're going to shift left, the reaction vessel will look more brown in color. If, let's say, we decrease temperature, so therefore you want to increase temperature, and the only way that you can do that is by shifting right, because you'll want to favor the exothermic reaction. So therefore, by shifting right, if we look at it in terms of a color change perspective, it's going to become less brown in color. It's not going to become colorless, because colorless is not a color, right? So that's how you want to phrase it. If you literally write colorless, which I did when I was practicing, you will lose marks. So you don't want to do that. If, let's say, we're talking about pressure, remember that pressure is inversely proportional to volume. So therefore, if you increase pressure, you decrease your volume. And then if you decrease volume, you increase pressure, and vice versa. All right. If, let's say, we increase pressure, then that means we want to shift to the reaction where we have a decrease in pressure by Le Chatelier's principle. We have a 2:1 molar gas ratio. So therefore, because we're increasing pressure, we want to shift right. By doing that, you have less particles in the system because you're going from 2:1, right? If you have less particles in the system, you're going to have less pressure, because pressure is pretty much just like particles like hitting the reaction vessel. So that's how you would want to structure your answer for pressure questions. Talk about the molar gas ratio and then explain how you have less particles, so therefore you're going to have less pressure. If, let's say, we decrease pressure, then we want to increase pressure. So we're going to favor the side where we have more particles, right? Because then more particles hitting the reaction vessel means more pressure. So therefore, the reaction would shift left. And as a result, you would have more NO2 particles within that system. So you just want to favor whichever side that will help to increase collisions. And in this case, it's the reactant side. If we look at concentration, if, let's say, we're going to increase the concentration of NO2, that this is pretty straightforward. it's just going to try to decrease it. And the only way you can do that is by shifting right. So that's pretty straightforward. And then if we increase the concentration of dinitrogen tetroxide, again, same thing's going to happen. We want to decrease the concentration, so therefore it will pretty much just shift left. Again, note that in these kinds of questions, it's really important that you talk about color changes if they do ask for it. And again, if let's say we're shifting left in this case, then it's just going to become more brown. All right, now let's jump onto Slido. And I do have a question for you guys. Let me activate the poll and we will go from there. I'm just gonna see what I can do with Slido. All right. Have a go at this question. So I've put up the question there as well. And it's asking what happens when the volume of the reaction vessel is halved. Okay, most people are saying C. Some people are saying A, some people are saying B. Just wait if more people want to put in their responses. I think most people are saying C though. I'm just gonna see if anyone else wants to put in their responses. Some people are saying A as well. Okay, and then there's a few people that is saying D. All right, let me explain it. So it's asking what happens when the volume of the container is halved. Whenever we're talking about volume, I like to relate it to pressure because I just find it easy to explain that way. If we have a decrease in volume because we're halving it, we're going to have an increase in pressure, right? And if we look at the equilibrium, we have a 2-to-1 molar gas ratio. So if we're increasing pressure, we want to decrease it. And the only way that I can do that is by shifting right, because you're just going to have less particles overall within the system. And that's why the correct answer option is C. If, let's say, you favor the reverse reaction and you have an increase in pressure, that's just going to continuously increase the pressure because from like a 1 molar gas ratio, you're going to 2, right? So it cannot be A. And then for B, it's incorrect because you will obviously have a change because you have a difference in molar gas ratio. In the event that, let's say, it was just like a 2-to-2 molar gas ratio, then it would be no change. But since you're having a difference, then you're going to see a change. So that's why B is not correct. So yeah, that's pretty much how this question would work. All right, let's get back to our next question. All right, so like I said, it's C. The next question is also on Slido, so let me activate that. I think it should work now. All right, this question is asking what conclusion can be drawn from this observation. Okay, some people are saying A, and then some people are mentioning B. Okay, give it more time so that more people can read this question, and it is pretty lengthy. All right, most people are saying A. And let's go through it. So A is the correct answer. And if we look at the observations that they've given, so at room temperature, it's light brown, and then at higher temperatures, it's a deeper brown. So therefore, at higher temperatures, it is shifting left, right? Because nitrogen dioxide is brown, and then dinitrogen tetroxide is colorless, right? So therefore, you know that in higher temperatures, you want to decrease the overall temperature by LCP. So therefore, it will favor the endothermic reaction. So from there, we can deduce that the reverse reaction in this equation is endothermic, right? It can't be the forward reaction, because if the forward reaction was favored, then that means it would become lighter brown at higher temperatures. And in this case, that's not happening, right? It's becoming a deeper brown. And then C and D is kind of irrelevant in this, really, because yeah, it's not really that relevant. Mainly A or B is what you're trying to deduce from here. So yes, A is the correct answer. All right, let's move on now to our next topics. Alrighty. Let's look at Le Chatelier's principle, but also in like an equilibrium. So this question is asking changes in concentrations of these substances in a vessel, and it's asking what changes are happening at the marked times. So if we look at the question, it's asking what changes are happening. So therefore, you can see at T1, only the concentration of N2 is increasing. So therefore, they're probably injecting nitrogen dioxide gas, nitrogen gas into the vessel. If we then look at T2, the concentrations of all three are increasing. So therefore, something that could happen is that you're decreasing the volume of the reaction vessel. And then finally, for T3, you have a gradual increase of ammonia as well as nitrogen gas. But you have an increase of hydrogen and nitrogen, but a decrease in ammonia. So that probably indicates a change in temperature. If we have an increase in these two, but a decrease in this, we have to look at our delta H. So therefore, the reaction is probably shifting left. If the forward reaction is exothermic, the reverse reaction is endothermic, so you're probably increasing temperature in this case. So you want to be looking at temperature when you're seeing gradual increases in like this. If you're only seeing an increase in the concentration of one reagent, then look at whether you're injecting something into the reaction vessel. And then finally, if you have an increase of all three, you want to be looking at pressure or volume. All right, let's move on to the equilibrium constant. So the equilibrium constant is pretty much a numerical value in order to express like what exactly is going on at equilibrium for a certain temperature. So just remember that equilibrium constants will change according to temperature only. So if we look at what the equilibrium constant would be in this case, we're pretty much just writing products over reactants, and the concentration, or not concentration, sorry, the number at front would pretty much be the number that's being squared. There is a way to derive this, but that is out of the scope of the year 12 syllabus, so don't worry about how you're getting squared and stuff. And also, like I said, if you have nothing at front, there's nothing that's going to be squared or like cubed or whatever. It's just going to be to the power of 1 over the reactants, and therefore it'll just be NaCl in this case, square brackets, and then squared because we have a 2 at the front over here. All right. In Mod 5, you guys also look a bit at Ka, but this is mainly related to Mod 6 as well. We know that Ka represents the equilibrium constant, so pretty much the ionization for acids though. And this only applies to weak acids, not strong acids, because strong acids have 100% dissociation. So therefore, it's a forward reaction, it won't form an equilibrium. In order to represent acid ionization, this is typically how you do it. So you have Ha as an acid reacting with water, going to A minus plus H3O plus hydronium. Not typically H plus. Like I know it's very like interchangeable, but the Bronzadari version is preferred in comparison to Arrhenius, so I would just recommend you stick with H3O plus. And here you don't write water because water does not have a change in concentration. Also, now that I'm reading it, I note that water is written as AQ. You would typically write it as liquid, not AQ. But the rest of the species would be AQ. So it's pretty much the same thing as to how you would write an equilibrium constant normally. So you have products over reactant, so A minus times H3O plus over HA. And this is also very useful in finding like concentrations of like the pH or like the concentration of hydronium, and also just showing how much it's really ionizing. You also have KSP. So KSP is covered like in detail in Mod 5. And this is pretty much known as a solubility product. So this can show how much a salt is really being dissolved within solution. And typically this is how you would represent the equation of a salt being dissolved. So you have, in this case, we have lead sulfate. So PbSO4 solid in equilibrium goes to Pb2 plus AQ plus SO42 minus AQ. And since it's products over reactants, in this case, you really can't include the reactant because it's a solid and that won't have a variable concentration. So therefore, it'll just be the products in this case. So it'll be Pb2 plus and then SO42 minus, and in this case everything is just like 1-to-1, so therefore you don't need to write anything as a power, but if you do have a number at front, then make sure you put it as a power. And because you're not really including the solid, it really shows how the salt is being dissolved and how much it really ionizes in that sense. So yeah, this is how you would pretty much do KSP questions. All right, now let's move on to questions. This is also a bit of Mod 6, as you can see, because it relates to pKa. It's asking you to find the pH of a 0.5 solution, molar solution of acetic acid. Let me put the question on Slido. Okay, someone got 2.55. In my solutions, I always do to the lowest number of sig figs. So you can do that if you want. So yeah. And it's also recommended that you do it that way, just so you never know what the question is going to be that they're counting for sig figs, right? Good. So one person wrote 2.6. We'll just see if anyone else wants to put in their responses. Okay, one person got 4.5, and then most people are getting either 2.55 or 2.6. Round it up. You wouldn't typically have to write if it's rounded up or rounded down. That should be fine. Alright, I'll just wait like a minute or more if anyone else wants to put in their responses. 5.1. Okay, I think some people are getting like pH is 4 to 5. Yes, you are correct. For anyone who's doing pH calculations, it's always going to be decimal places. pK is sig figs, by the way. It's not decimal places. So yeah. I do have the solution though, so I will explain through it. Okay, I think that's pretty much it. So let me close the poll and then we will go back. Slido is being really annoying today, so I'm sorry if I'm being really slow. Alright, let's go back. So, if I go back to the question. It's loading. Okay, there we go. Alright, so this question requires you to manipulate a bit of data. So it's talking about the pK of acetic acid, and then it's asking you to find the pH. Whenever you're doing pH questions, the lowest number of sig figs is pretty much the number of decimal places that you're going to be using. In this case, we have 0.5 here, so therefore that's 1 sig fig. So therefore you round your answer to 1 decimal place. So just make sure you note that down at the start. So for these kinds of KEQ questions, it's always good to write down an equation. I just wrote down the ionization of acetic acid, so CH3COOH, AQ plus H2O liquid goes to acetate, aqueous plus hydronium. So they have given us the concentration of acetic acid initially, so that's 0.5, and then we don't know the concentrations of acetate or hydronium because they haven't ionized yet, so therefore it's 0. And therefore you write down the change as well. When it's ionizing, it becomes minus X, and then since it's being ionized, acetate and hydronium is plus X on both sides. X just represents like an arbitrary like number that you want to show in terms of change. So you could just say like let X be change in concentration of acetic acid. So that's why it's minus X here and then plus X for these two, because everything is in a 1-to-1 molar ratio. And then you write down your equilibrium. So you have 0.5 minus X and then X and X. They've given the pKa, so therefore you can find Ka. If pKa is 4.8, then Ka is 10 to the power of negative 4.8 because pKa is negative log 10 Ka. So remember your log laws. You can also use small change assumption because Ka is pretty small, so therefore 0.5 minus X would just be equivalent to 0.5. You don't want to use the equal sign. You would write down this like little squiggly equal sign over here. So therefore you just plug everything into the KEQ expression. You have X squared on both sides, so that's X squared over 0.5 because we're writing over reactants, and you just equate that to your KEQ and then rearrange it so that X is the subject, and therefore you should be getting an X value of 0.0028 molar. And then if you need to find pH, just negative log 10 of X, because X is pretty much hydronium in this case. So therefore, your answer should be 2.6 dP. But I think when I was doing this question, I would have gotten 2.5 or something as well. So yeah, if this was a sig figs question, then you would lose a mark if you're not writing to the correct decimal places, sig figs, whatever. So yeah, just do it in all questions. That's just my rule of thumb. All right, let's move on to the next question. Let me activate it on Slido. I think it should show up now. There we go. Note that solubility is asking in grams per liter, so just be aware of that. Okay. These answers are a bit different to what I have. So I'm gonna check my own answer now. Just to make sure. Okay. Some people are getting different answers. Just make sure you have converted into grams per liter as well. Okay. Okay, hope one person's gotten my answer. Okay, good. I nearly got scared for a second. There's a bit of variety here. Okay, some people are getting around 1 point something. And then some people are getting 2.2 times 10 to the power of negative 9. I think whoever wrote 2 times 10 to the power of negative 9, that's the answer in moles per liter, not grams. So you're almost there. All right, I'll just wait if anyone else wants to put in their response. Okay, most people are getting around like 1 times something times 10 to the power of negative 7-ish. All right, I'll wait like a minute maybe, and then we'll move on. Okay, there's just a few people typing, so I'll let them finish off. Okay, cool. Alrighty, most people got 1 point something times 10 to the power of negative 9. Let me close this poll and let's go back. Alright, so for those who got like 1.41 times 10 to the power of negative 7, that's all correct. For anyone who wrote 2 times 10 to the power of negative 9, I think you're referring to the molar concentration, not like molar solubility, sorry, not solubility in grams per liter. So the way you do these questions is I always like to do ice tables, just makes it so much easier. So you start off with writing your equation. So we have aluminium hydroxide, which has a formula of AlOH3 solid goes to Al3 plus and 3OH minus. You don't need a 3 here. I don't know why that's there. So just correct it if you guys have the copy of the slides. All right. Okay, so like I said, you want to have like a value of x, right? So I just said that let x be the concentration of Al3 plus. So initially, when we're dissolving a solid, we're not really going to have the concentration of either one. So it'll be 0 at the start. And then when it's being dissolved, it'll become plus x for aluminium and then plus 3x for hydroxide because it has a 1 to 3 mole ratio. And then at the end, it's just going to be x and then 3x. So for solubility, you're always just trying to solve for x. So you just put that into your KSP equation. KSP in this case would be x times by, so the general equation would be AO3 plus and then OH minus cubed, sorry. And therefore, if you sub in your x values, it'll be x times 3x whole cubed, just the 3x. So therefore, it'll be 27x to the power of 4. And if you equate 27x to the power of 4 with 3 times 10 to the power of negative 34, you should be getting x as approximately 1.82 times 10 to the power of negative 9. If you guys got like other answers, I think what might have gone wrong is maybe you didn't cube the 3x over here, or you might have accidentally not calculated your final KQ expression correctly, or something along those lines might have been the reason why you got it wrong. So therefore, from here, from molar solubility, if we want to go from moles per liter to grams per liter, you need to times it by the molar mass of aluminium hydroxide. And if you do that, you should be getting solubility as approximately 1.42 times 10 to the power negative 7. For those who did sig figs, it's just going to be 1 times 10 to the power of negative 7 to 1 sig fig. And again, another point of error could also be if you incorrectly calculated the molar mass of aluminium hydroxide. All your molar masses are within the periodic table, so just double check as well in these kinds of questions. All right, we have one final question. Let me activate it on Slido. All right, I think it should show up now. Okay, I understand. This question's kind of hard. But I will go through the solutions with you. We'll just see if anyone else wants to put in their responses. I'm sure everyone's just calculating. Can we have a hint? Okay, let me think. This is a common ion effect question. There is a common ion here that you would have to input into your ice table. Hopefully that helps. I don't know if that helps. Someone got 0.575. Okay. Yes, I will explain the last step for the last example. Someone got 5 point. Oh, just wait. 5.7 times 10 to the power negative 7. All right, 0.22. Okay. I'll just note down for the person who wants me to explain the last step. Okay, I think I will just explain it because I think people are struggling on this question and I can understand because it's a bit hard. I feel like KSP questions are always the hardest out of Mod 5 in general. Okay, I'm just gonna let that one person who's typing. Oh, jokes. All right, you know what? I'll just go through it. Let me stop the poll and then we can go through it together. All right, so like I said, this question is a common ion effect question. And if we read the question, let it load, you can see that we have magnesium carbonate and sodium carbonate. Common ion is carbonate, and they've already given the concentration of that solution. In this case, it's 0.001. So therefore, we want to start off with writing the equation for the dissolution of magnesium carbonate, so MgCO3 goes to Mg2 plus CO3 2 minus, both in aqueous solution. And we also know that we have a solution of sodium carbonate. So therefore, since it's 0.001 of sodium carbonate solution, the concentration of carbonate is also going to be 0.001. Again, we use our change as x. So in this case, it's going to be plus x for both. Both of them have a 1-to-1 mole ratio. So therefore, it's just going to be x and then 0.001 plus x. If you want to get the KSP of your magnesium carbonate, go to your periodic table. So not periodic table, sorry, data sheet. And you'll see like a bunch of KSP values. So that's where you get it from. And that's where I got it from. So 6.82 times 10 to the power negative 6 is the KSP. And you can use small change assumption here because times 10 to the power negative 6 is relatively a small value, right? So therefore, you can just let 0.001 plus x as 0.001, write down it as small change assumption, plug it into x, not plug it into x, plug it into KSP. So you plug in x and then 0.001 because you don't need to do 0.001 plus x because of small change, right? And therefore, if you rearrange so that x is the subject, you should be getting approximately 0.00682 molar as your x value. And now we need to find what mass of magnesium carbonate can be dissolved. So therefore, you need to convert it from moles per liter to grams per liter. So therefore, you should approximately be getting 0.57 grams per liter. So therefore, if you round it up, in 1 liter of solution, you should be getting approximately 0.58 grams of magnesium carbonate being dissolved. I don't really do sig figs for this question, but if you do sig figs, it's just going to be 1 sig fig for this question. So that's how you kind of work it out. So if it's asking determine what mass of blah, blah, blah is being dissolved, you want to be writing the KSP equation and equilibrium expression, an equation for whatever salt is being dissolved, not the common ion that's within the solution. So nothing about sodium carbonate, so only about magnesium carbonate. If you guys have any questions that you need me to explain, let me know and I'm more than happy to do that. All right, I think we're running a bit late, so let me go through mod 6 now. Mod 6 is pretty much just acids and bases and a bit of KEQ calculations as well. You also look at like different acid and base models that you have explored over time. So let's start off with Lavoisier. And this guy pretty much just said that in the presence of oxygens that it's caused by nonmetals, it caused acidic properties to pretty much be formed. And it also demonstrated that nonmetal compounds that contain oxygen do produce acids. However, it doesn't really explain why metal oxides could also be acting as a base. Davy pretty much looked at the electrolysis of HCl, and it kind of deduced that most acids should contain hydrogen, and that acids and bases react to form salts. But it did not explain why compounds that contained hydrogen were not actually acidic. So, for example, like methane. Arrhenius and Bronsted-Lowry is the main two that we look at in chemistry that you would really be asked to compare. Arrhenius proposed that acids pretty much dissociate into H+, bases into OH-, and also proposed that like strong acids dissociate more in comparison to weak acids. However, it does not explain why certain substances act as either, like a base, for example. So for example, or also why like there's some bases that don't even dissociate into OH-. An example is ammonia. And then Bronsted-Lowry kind of is the main one that we use anyways, and defines acids as a proton donor, proton being H+, and then base being a proton acceptor. However, it does not explain why there are certain acids and bases that don't have H within their structure, hydrogen within their structure, actually act as an acid or a base. And that's, for example, boron trifluoride. I think it's a Lewis acid, and it doesn't have hydrogen in it. So Bronsted-Lowry can't really explain the nature of that acid. And that's where the Lewis acid-base theory comes. You wouldn't really have to know it, but just for like the sake of covering everything. A Lewis acid is pretty much an electron pair acceptor, and then a Lewis base is an electron pair donor. So you can kind of see that it's a bit different to bronzolari in the sense that it's kind of swapped around and it talks about electron pairs. But that's really uni level, so you don't have to worry about it too much. All right, so now that we've explained Ronsolari theory, in order to just, I think I've already explained this, but I'll just say it again. If you want to write down the equation of a weak acid, then you want to react it with water and then show that it goes to A minus and H0 plus. Again, water has to be liquid. And then for strong acid, it's just pretty much the same thing, but in full ionization. So therefore, you write it down using a forward arrow. And then for weak base, it's again equilibrium. So you have a base reacting with water to produce hydroxide. And then for a strong base, it's pretty much the same thing, except you write down a forward arrow pretty much. In terms of neutralization reactions in relation to Ronsolari theory, you would pretty much write it as irreversible reactions, sorry. So therefore, if you're having an acid base reacting, don't write it as like an equilibrium expression, because that is wrong. So just make sure you do it that way. And in a sense, what neutralization reactions really do is that you have H plus with OH minus reacting to form H2O. One thing to also note is that water can also exist as an equilibrium. So H2O can also, this is pretty much could also be expressed as an equilibrium, but for the sake of neutralization reactions, we're writing it as a forward arrow. And they pretty much all have an enthalpy of negative 57.3 kilojoules per mole. All right, I don't know if we have time for practice questions because we are running a bit late. So let me just quickly skim through as to how much we have. We do have a few, so maybe if we have time, we'll come back to those practice questions. But for now, what I'll do is I'll hop onto your questions. So we have a few over here. Keep on putting in your questions. I'm more than happy to answer them. So the first question is asking if the question does not state whether to use LCP or collision theory to explain a change in concentration or rate of reaction graph, should we mention both? For rate of reactions, it's better to use collision theory, in my opinion. It's kind of hard to do with LCP, in my opinion. Because like collision theory can explain like the energy of the particles, right? And that really helps at rate of reaction. For change in concentration, it's better to use LCP. So if you see anything about concentration, pressure, volume, temperature, immediately define LCP and use LCP to explain your response. If they ask for collision theory, then put it in. But if it's for like a rate of reaction question where you really need collision theory to explain it, then it's better you define the three like terms of collision theory. So we're really talking about collisions happening at the correct molecular orientation and colliding at sufficient energy. So sufficient energy means energy that's equal to the activation energy or that's more, right? So that's how you kind of gauge as to whether you should use LCP or collision theory. Another person asked why, let me clear this question. I don't know why I can't clear it. Let me clear it on my phone. Also, if you guys, I think you guys are already like bumping up the questions though. If you really like the question, then just hit, I think there's like a like button. So then I can answer it more quickly. So that's fine. I think I'm just gonna delete that question. I think I archived another question. I'm just gonna put it back. All right, someone asked, why does equilibrium constant only change if there is a change in temperature and not in pressure or concentration? Thank you. So whenever you have it really relates to stoichiometric ratios. I know it's a bit confusing. So if you have a change in pressure or concentration, it will shift, but it will rearrange itself so that it's within its stoichiometric ratio. So ultimately, that ratio is not going to be affected because in essence, an equilibrium constant is pretty much like a ratio, right? When you think about it, it's just dividing a product of a reactant. Whereas in temperature, it kind of changes that stoichiometric ratio. So that's why equilibrium constants are affected by temp and not by pressure or concentration. Hopefully that answers your question. I'm just gonna clear that. Someone asked, okay, what colors are we supposed to memorize? For mod 5, really, like, I know in the syllabus dot points, they give you examples of equilibriums that you're going to explore. So, like the cobalt to hexahydrate equilibrium, the nitrogen dioxide dinitrogen tetroxide equilibrium, and also like other examples of irreversible equations. For all of those, you want to be memorizing your colors. For solubility, you want to be memorizing colors of key precipitates. So, for example, like lead iodide is like a canary yellow precipitate. So, you want to be memorizing precipitates of example reaction that's already within the syllabus stop points, as well as like the colors of your precipitates. So hopefully that answers your question. That's a very like broad question as well. There's like a lot of like niche things that you have to memorize, but if you want to categorize it, that's how I would go. If like you're not meant to know it, they would literally give you the color, so don't worry too much. Some people are just asking more questions, so let me bump up their questions. Okay, someone's asking, how do we know what states reactants and products will be? So I feel like some of them is just like a given. You just have to know because of the syllabus. So for example, acids and bases are always going to be in solution, so they're AQ. And then for certain equilibriums, so like the dinitrogen tetroxide and nitrogen dioxide equilibrium, it's going to be like a gas. And then for like KSP questions, you have a solid going into aqueous, right, into its ions, right? So you kind of have to know those. If it's like something like really absurd and you don't know what to write, you should look at the question because they should be giving that to you already. But for general things like acids and bases, which are always in solution, and then for some reactions that may be gaseous, you should be able to know them. So look at your syllabus stop points, and look at the equations that they've and like equilibrium reactions that they've asked you to explore, and then go from there. Alrighty, let me clear a question. Let me clear that question, 1 second. Okay, someone asked, how do I convert from moles to grams per liter? So to go from moles to grams, you need to times it by the molar mass of the substance that you want to convert to. So for example, if I need to convert like a solution concentration of sodium chloride from moles per liter to grams per liter, then I times it by the molar mass of sodium chloride, which I will find in my periodic table. So yeah, that's how you do it. Use the formula N equals M over MM. So you'll know what to do from there. All right, let me clear this question. Someone asked, if we have no idea how to approach a question, how do we get something down? Okay. Okay. Even if it's just like a relevant like equation, that would probably be like a mark. A relevant definition would probably be like a mark. So try to write down key definitions and equations if you sort of know them. Otherwise, try just doing whatever explanation that you're aware of potentially. That's what I used to do. Like if I had absolutely no clue like how to write down a question, I would just try to write down my best interpretation of that question and pray to God that hopefully gets me marks. And usually would get me like at least a few marks if I had like some relevant ideas. So for example, like a relevant definition. So that's how you would write it down. All right, let me clear that question. Someone's asking, why are we assuming a small change? Good question. So small change assumptions used when your KEQ is like super tiny. So if it's something less than like 10 to the power of 3, so we're talking about 10 to the power of 4, 5, 10 to the power of -4, -5, -6, things like that. That means pretty much you don't have a lot of products on the right-hand side. So whatever is on the right-hand side, you can assume that it's negligible, that change, and that's why we're using the small change assumption. So if you really want in your answer, you could say that since this KEQ value is of a value that's less than like 10 to the power of -3 in magnitude, then you can use small change assumption. So hopefully that answers your question. Okay, I think I'm gonna have to stop for now. before I let you guys quickly go on your break, I just want to talk a bit about private tutoring. ATAR Notes does offer private tutoring, and I personally offer Chem, English Advanced, as well as Bio. So if you want, you guys can do book an info call, and you will get matched up to your tutor based on like our availability as well as your availability. All right, now it's break time. I'll give you guys a 10-minute break, so I'll see you at 10:50. All right. Hopefully you guys had a good break and getting back to your seats. In the meantime, I'll just quickly go over as to what Ed Unlimited offers. Currently, I mean, like I said earlier, it's pretty much just like a place where you can get study guides. And currently, if you use my code Mahima HSC, you do get off like free for 21 days. And I think it'd be really useful, especially if you guys want extra practice questions, not only for chemistry, but also for all your other subjects. But if you guys do prefer the printed versions, I don't know why that took so long. I love the printed versions as well, personally. I just find it easier to write on as well. We do have a 50% off code at our 800.com shop. And if you use the code 15%, not 15%, 15 September on checkout, you will get 15% off. So if you want, do go check that out as well. All right, so we've covered mod 5 to 6 so far. Unfortunately, I couldn't go through the questions because we're kind of short on time, but we can go through mod 7 and 8. Mod 7 is pretty much your organic chemistry, I guess just like realm. In terms of nomenclature, let's start off with the first step, and it's always trying to find the longest carbon chain within the molecule. So depending upon the carbon chain, you're also going to have different prefixes. So for one, it's met, and then from there it's eth, prop, but, pent, hex, hept, and oct. It's not sept for 7, it's hept. So I always get it confused between the two. So I'm just pointing that out as well. And here, in this case, if we figure out the longest carbon chain, it'll be 1, 2, 3, 4, 5. Therefore, since it's 5, it's going to be pent. Next thing is to determine what the major functional group is based on priority. So we start off with carboxylic acids, then goes to esters, amides, aldehydes. Then from there, it's ketones, alcohols, amines, and alkenes and alkynes. These are always like the lowest preference. So you want to figure out which suffix. In this case, it's going to be. In this case, it's going to be an alcohol. And then from there, you also want to be looking at halogens as well. And most of the time, halogens are just going to be like a group that's just being added onto. So in this case, it's OH, and like I said, the next thing you also want to be looking at is figuring out your locants. So that's also for the OH and the fluorine over here. The one that is taking on the major prefix is going to have the lowest locant number. So therefore, we want to start off with this carbon. So therefore, the OH group is going to be 1. Also, you want to be looking at what the locant is for fluorine. So if this is 1, then if we go from 1, 2, 3, 4, then fluorine is going to be attached to the 4th carbon. You might also have a point of differences when you're looking at the total number of locants and how you want to arrange that. So let's look at it together. We use point of difference when you have like multiple like locants needed. So in this case, we have 2 chlorines and as well as a fluorine over here. So you want to be looking at the locants for all of them. It could be either like 1 and then 2, 2 for the 2 chlorines, then 3, 4, 5, 6. So it could be 2 to 6, or it could be 1, 2, 3, 4, 5, and in this case it's 2, so it's going to be double 5s. And in these kinds of questions where you have 2, you want to be looking at the point of difference, not the total sum. In this, the sum is 11, but in 2 to 6, the sum is 10. So therefore, even 2 to 6 is preferred. 155 is going to be like preferred in the sense that it has a lower sum. The actual thing we're going to be looking at is point of difference. So therefore, you want to be taking 155 rather than 226 overall. Hopefully that makes sense. Like you just look at like overall which one has the lowest number. You don't look at the sum. And then from there you can figure out which set of locants you want to take. All right. Also, another thing to note is that you want to list your prefixes in alphabetical order. So for example, if you have like chlorines and then a fluorine, then chlorine will be named first, followed by fluorine, etc. So in that case, if we look at this compound, we have fluorine, and then we have a alcohol. So therefore the alcohol would be the first preference. So we want it to be having the lowest locant, so therefore it'll be 1. And if we look at the longest number of carbons we have, it's 1, 2, 3, 4, 5. So therefore it'll be pent, so pentan 1-ol. And then you would just want to be naming the other groups that you have at being added on. So in that case, at the third carbon, we have a methyl group, and at the 1, 2, 3, fourth carbon, we have a fluorine. So therefore, it'll be 4-fluoro, 3-methyl, pentan, 1-ol. One thing to note is that between numbers and letters, you have a dash. Between letters, there's no difference. And then if you have two numbers joined together, like let's say if it's like 4, 4, then you will separate it by a comma. So if you don't write down the commas and dashes, you'll be losing marks. So make sure you know the differences between all of them. All right, now let's have a bit of practice for nomenclature. Let me put up this question on Slido. 1 second. It's just taking so much time. Okay, I think I put the question on Slido now. Okay, there we go. Have a go at naming this compound. So some people have written down their answers, so let's look at it. Most people are doing hextooine, which is good, so you've identified the correct thing. Some people are doing fluorines in front of chlorines. Remember, it's alphabetical order, so chlorine comes first, then fluorine. And if it's fluorine, there's 2 fluorines in this case, it'll be difluoro. So that is the correct answer. All right, hopefully that makes a bit of sense. So most of you guys have done hextooine, so you understand that this needs to be having the lowest locant. And then from there, you just look at the different kinds of like numbers that you have. This is not necessarily correct because you need to space it out in terms of your kind of, what is it called, commas and dashes. So these two are technically not correct, but the numbers are correct, if that makes sense. So therefore, if we start off with naming it, it'll be 1, 2, 3, 4, 5, 6. That will be your carbon chain. So therefore, you have a methyl group here at 1, 2, 3. And then at 4, you have a fluorine. And then at 5, you have a fluorine as well as a chlorine. So therefore, it'll be 5-chloro, 4, 5-difluoro, 3-methyl hextooine. Yes. Also, there would not need to be a comma between the letter and number. It'll be a dash. So just make sure you are very careful in those kinds of things. All right, let me stop the poll. Hopefully everyone understands how to name it. If you do have questions, just like shoot it away. I'm more than happy to answer. All right, let's try out this question as well. Let me put it up on Slido. Good. Someone wrote 3-methyl butanoic acid. Some people are writing 2-methyl butanoic acid. All right, most people are writing 3-methyl. I'm just gonna let whoever's writing their other answers down, and then we'll go through it. Okay. All right. So, for those who wrote 3-methyl butanoic acid, that is correct. Most of you have identified it's butanoic acid because the longest carbon chain is a 4-carbon chain, so therefore it takes a prefix of but. And then you also write acid, so that's good. And this is the acid group over here. The reason why it's not 2-methyl butanoic acid is because if you start from here, so it's 1, 2, and then it'll be 3, 4, then your locant for your acid is going to be on the 4th carbon. And that's not how it works. When you're naming acids, it's going to be always on the 1st carbon. So that's why you don't actually add a locant for your acid group over here. So therefore, 2-methyl butanoic acid is incorrect. So yeah. Another thing to note is I think someone wrote down the answers like this. I don't know if they're just like not bothered to write down the dashes, but I'm just gonna say it anyways. Make sure you write a dash between a number as well as a letter. And then for butanoic, you have a space between that and the acid. It's not joined together. I know I said earlier on that like 2 letters are going to be joined together, but acid's just separate, if that makes sense. So yeah, hopefully that has answered all of your questions. So I'll just close down the slider and then we'll move on. Alrighty. Okay. This pretty much summarizes what your numbering should look like. So yeah, the most important functional group gets the lowest locant number. If you have several locants, look at point of difference. And another thing to also note is that if you have several, like, I guess substituents of the same kind. So for example, like if you have 2 fluorines and add di, and then if it's 3, try, and etc. In terms of double and triple bonds, just make sure you know what the like suffix and prefixes are going to be. So for double and triple, it's going to be YNE, and then for alkenes, it's going to be ENE. And then sometimes if you have a double or triple bond that's after the parent chain, like prefix, then you would change it to something like buten, so EN. And then for alkynes, it's going to be YN. So that's only if you have like a double or triple bond within the structure itself. Punctuation is really important. If you like don't include punctuation, you're going to be losing marks because that's incorrect IUPAC nomenclature. So like I said, commas are between 2 numbers, hyphens are between number and letter, and then for the oic part and then the acid have a space, like I said. So that's the only exception that you really have here. All right, let's move on to properties of homologous series. You should have a rough idea as to how the boiling point really varies. So amines always have the highest boiling point, followed by carboxylic acids. Then you have alcohols, then ketones and aldehydes, and then the rest of them. So you have like amines, followed by haloalkanes, and alkenes, and alkynes. Those are the ones that have the lowest boiling points. The reason why alkanes have a higher boiling point in comparison to alkenes and alkynes, because alkanes are the most stable out of these three, because they have single bonds. And then alkenes are second most stable, followed by alkynes. They're the least stable. So really, if you need to like change its boiling point, then alkynes are going to have the lowest boiling point in that sense. So yeah, overall, in terms of all kinds of homologous theories, your melting and boiling points will increase as a molecule gets larger, simply because you're just adding more CH3 groups. So therefore, you're increasing the amount of dispersion forces within that compound. So therefore, you're having an increase in boiling point and melting point, because you need to break those intermolecular forces in order to actually increase it. And as you also increase the amount of carbons within a chain, it's going to decrease solubility. Because if you have more dispersion forces, you're making the molecule more nonpolar than it is polar. So therefore, you're going to have decrease in solubility, and larger liquid molecules are just more viscous than smaller liquid molecules as well. Viscosity is not really something we really talk about too much. It's mainly like what kind of intermolecular forces that are within the compound, as well as solubility rules. In terms of properties for alkenes, alkynes, and alkanes, like all of these are nonpolar, by the way. So that's just a common trait. All of these are insoluble in water because they're nonpolar. Alkanes are the most stable out of these, but remember, as you have more branched kinds of hydrocarbons, you're gonna have a lower boiling point, because if you have branching, then that means you're gonna have weaker dispersion forces, so therefore you're gonna have a lower boiling point. Also just note like which ones are gaseous. So for all of these, from like first carbon to the fourth carbon, they're all gaseous. So just make sure you are aware of that. And then alkenes and alkynes are pretty reactive, because that double bond or that triple bond is more unstable. So therefore it just likes to be broken into a single bond. So that's why it can react. Alkanes can react with halogens in the presence of UV light as well, by substitution. So just make sure you're aware of that as well if you're asked for reactions with alkanes. In terms of the rest, in terms of amines, aldehydes, and ketones, amines are basic. So if you're asked to write down an equation of how it reacts with water, then you would demonstrate that it dissociates into hydroxide ions as well. And because it's basic, it can react with carboxylic acid to produce amides. So that's really how amides are produced. Aldehydes, you know that they pretty much have that COO bond on the first carbon, and it can be oxidized further into carboxylic acids. Ketones pretty much have that COO bond in the middle of like a carbon chain, so therefore it can't oxidize any further. Just to note, aldehydes have a higher melting and boiling point in comparison to amines, and ketones have a higher boiling point in comparison to aldehydes. We also look at alcohols, carboxylic acids, and amides. In terms of alcohols, from methanol to propanol, it is soluble in water because it's mainly more polar. So as you increase the carbon chain, it becomes more and more non-polar. Ethanol is also known as a universal solvent, so just make sure you're aware of that. In terms of carboxylic acids, it's very like polar when you have it from methanoic acid to propanoic acid. And obviously, as the name suggests, it's acidic. Amides, on the other hand, are not acidic or basic, it's neutral. And it's also pretty soluble in water as well, like I said, because it has those two NH groups as well as a COO group, so it makes it very soluble. And it also has the highest melting and boiling points out of all the compounds that we have here. So just make sure you are aware of that. All right, let's talk a bit more about reactions. So when we're looking at reactions, you want to be looking at what the reactants are, what your products are, obviously, because you need to write down the equation, as well as like what catalyst you're using and any kinds of other conditions. So do we have like temperature or the presence of UV light, or do we have like an oxidant? So for example, potassium permanganate, so forth. All right, let's look at halogenation. So halogenation involves an alkene reacting with halogen to produce a haloalkane. This is an addition reaction, and that's basically because you're breaking the double bond. So just note that. If it is asymmetrical, so like the alkene is asymmetrical, you could have multiple products. You do not need to identify what's major product, what's minor product, I think, in the syllabus. I don't think I did personally. So just like know that you can have multiple products sometimes. So yeah. In terms of hydration, it's pretty much having an alkene producing an alcohol. And for that, you need a dilute acid catalyst. And again, it's also an addition reaction. You can see that the double bond is being broken to form an alcohol. So just make sure you're aware of that. Again, you could have multiple products, so be aware of that. In terms of like naming these kinds of products, just make sure that like you're not repeating the same thing again. So in terms of naming, because you want to have the lowest locant for the alcohol. So just be aware of that. Dehydration is the opposite. So therefore, instead of having a dilute acid catalyst, you have a concentrated sulfuric acid catalyst. So yeah, the way I like to remember it is that dilute means like more water, so hydration. Concentrated means dehydration. Also note that the reason why we're doing these kinds of catalysts, specifically sulfuric acid, is because sulfuric acid is a dehydrating agent. So it likes to absorb a lot of water, especially if it's concentrated. So therefore, if it's dehydration, you have an alcohol going to an alkene, pretty much. Also note that in this, you can obviously have multiple products because the OH can be removed so that the double bond goes here, or that the OH can be removed so that the double bond goes here. So there's two ways where you can do it. So again, if you have multiple products, which it often will be having multiple products, just be very careful. Substitution for alkanes is pretty straightforward. All it is pretty much having an alkane reacting with a kind of halogen in the presence of UV light, because UV light needs to kind of help the bond be broken. Otherwise, it's very stable. It's not going to break. And what happens is that you have one halogen, not both, being substituted onto a cup, like a hydrogen. And you can see here that a new product forms, a halogenated alkane, pretty much. So again, be careful. There might be multiple products for this as well. So just be aware. All right, in terms of oxidation, this involves alcohols. So for primary alcohols, it pretty much oxidizes into a carboxylic acid. Aldehydes are an intermediate product. So unless the question asks you for it, just write the oxidation reaction of a primary alcohol from primary alcohol to carboxylic acid. For secondary alcohol, it does not produce an aldehyde. It produces a ketone. I don't know why it's written like that. So let me change that. So just correct it if you guys have access to the slides. A secondary alcohol produces a ketone, and then tertiary alcohols don't oxidize at all. And in order for these reactions to occur, you need an oxidizing agent, so you need permanganate or dichromate, so Cr2O7. So yeah, this pretty much just summarizes all the different kinds of reactions where you have like it going from aldehyde to carboxylic acid. So yeah, and secondary alcohols go to ketones. So yeah, like I said, if they ask for aldehyde, write it down. Otherwise, don't typically write it down. Otherwise, they might think that you're not fully aware of the reaction. In terms of esterification, which is pretty much a reaction between carboxylic acids as well as alcohols, there are a few conditions that you should be mentioning within your reaction. So we know that the catalyst here is just concentrated sulfuric acid. And also, a difference is that a lot of these are just like forward arrow reactions, right? So in this, it's an equilibrium. So write down your equilibrium arrow. In terms of esterification, we do have something called reflux. And if you've seen the setup before, it's pretty much just like a condenser tube that has like water flowing into it, and that just helps to cool down the products and return it back to the reaction vessel. or like the little flask that you have, the round bottom flask. And you also have concentrated sulfuric acid. Like I mentioned, it's a dehydrating agent. So therefore, it removes water, and by removing water, it forces the reaction to go right, and shift right. You also have boiling chips, and these are just pretty much like ceramic chips that help to prevent something called bumping. So that's pretty much like liquids that are really heated, just like kind of like exploding pretty much. And also helps to have a smooth boil. So there's a lot of safety considerations that we also have within esterification that you may be also asked to explore. So be aware of how these conditions work, especially for esterification. All right. Sometimes questions may also just give you an entire roadmap, and they may ask you to write down the structures of these kinds of questions. I don't know if we have the time to do that, so I think we're just going to move on. I'll also answer questions within the second content block, by the way. So if you do have any questions, just keep on like putting it through, and hopefully I do have the chance to answer them. All right, let's move on. In terms of module 8, it's very like interlinked with all the other modules that you've encountered. So make sure that you have a good understanding of those before you move on to mod 8 as well. In mod 8, you may be, actually not you may be, you will be asked to identify differences in cations and anions, and this is really helpful in the form of flowcharts. Overall, in terms of cations, you're really just asked to identify the ones that are typically insoluble. So for example, like in order to identify chloride, you would react it with, for example, silver. And if it reacts with silver, it'll produce silver chloride, and that pretty much decomposes under UV light. It turns brown pretty much. For like sulfate, you could add barium ions, and that's pretty much just going to produce a white precipitate. And then for like hydroxide, you could add something like copper, which would cause it to produce like a blue precipitate. For hydroxide, it's pretty versatile because it will produce a lot of precipitates, right? Because hydroxides are mainly insoluble. So that's how you can distinguish these kinds of cations. For anions, you would typically start with adding an acid. So you would, for example, add HNO3, and what would happen is that you would have carbonate reacting with this acid to produce bubbles. So immediately you know that carbonate's out of the question. If you add copper, you can also help to distinguish hydroxides. If you add barium, then it will react with the sulfate, right? So then you'd know you have barium being present. You also do the same thing for cations. And if you do add sulfate, to distinguish between barium and calcium, you would do a flame test. So just be aware of that. For barium, it's apple green, and for calcium, it's brick red in a flame test. So adding on to someone's question about colors, you need to know flame test colors as well. So just be aware of that. If you add lead, what will happen is that it would react with chloride or bromide, and then for iodine, it's just going to react with lead and then produce the yellow color that I was mentioning about earlier on. If it reacts with chloride or bromide, it'll produce a white precipitate. It's very like hard to distinguish in color. And then if you want to further distinguish it, you can add silver. So silver chloride is white, and then the silver bromide is like a palish yellow, so you can distinguish it from there. All right, let's move on to HNMR. So this is pretty much an example of your HNMR spectrums, and hopefully, if you guys remember, you would need to kind of identify the differences between these kinds of spectrums. If we look at the HNMR spectrum, just remember that it will pretty much be representing as like peaks like this, like sets of peaks really. And it's based on the N+1 rule of spin-spin coupling. So pretty much these do not represent the carbon themselves, they represent the neighboring carbons. Let's start off with the OH group. And the reason why the OH group is represented as a singlet is because the hydrogen is attached to an oxygen. So therefore, you don't really regard like the oxygen be attached to carbons. You discount that. So therefore, it's attached to no other carbons that contain hydrogen. So therefore, it's seen as a singlet. The CH2 group is attached to a CH3, which contains three hydrogens and then an O, so an oxygen. So therefore, by the n+1 rule of spin-spin coupling, you'll be seeing a quartet, which is pretty much a set with 4 peaks. And then for your CH3, it's attached to a CH2. A CH2 has 2 hydrogens, so therefore by the n+1 rule, you would be seeing a triplet. And that's how you kind of deduce which one's which. Sometimes you may be given something called a relative signal integral, and that just like tells you how many hydrogens there are on the original like carbon itself. So for example, if you want to know a relative signal integral for this quartet, it'd be 2, which represents the CH2. Hopefully that makes a bit of sense. Moving on, we also have CNMR. In terms of CNMR, it's a bit different to HNMR because you're not going to really see like splits like this. You're just going to see peaks like this, and each peak represents a carbon environment, by the way. In this case, I really only have 2 carbons, so therefore I'm going to see 2 different carbon environments. And if you want to know which one's which, you look at the difference in ppm values. The further it is, so the larger it has a ppm value, the more electronegative it's going to be. So therefore, the CH2 would be representing this, and then because the CO bond is represented, I think by a number between like 50 to 60-ish. And then the CH3 would be represented by this peak here at approximately 15 ppm. One thing I'd like to also note is that in HNMR, each set of peaks represent a hydrogen environment. So I have 3 sets of peaks here, which corresponds to the 3 hydrogen environments over here. So you want to be mentioning all of these within your responses. And also mention the n+1 rule of spin-spin coupling every time you're mentioning a different like set of peaks. Otherwise, you'll be losing marks, and we don't want to be losing marks. All right, we also look at the infrared spectrum, and this is really useful when we're looking at the like different kinds of bonds that are present. Typically for infrared spectrums, we don't really go past 1500 and below, simply because it's something known as the fingerprint region. And this is where bonds start to overlap, and it can get a bit confusing when trying to interpret it. But if like you really have no other option, then you can analyze fingerprint. So it should be fine. But typically steer away from it. So if we want to figure out what kind of bonds we have, this is pretty much on your data sheet, but just from looking at it, we can see that we have a really broad peak here, and that represents the OH group over here. And if you look at your data sheet, it'll correspond to it. You also have CH bonds being present, and that's present within the sort of sharp, like almost sharp peaks here, approximately at 3000, and those represent the CH groups. So this is the OH, and this is the CH bonds being represented within the IR spectrum. You also can look at mass spec. Mass spec is really nice when you're trying to determine like sort of what kind of fragments are really present. So mass spec has 2 key features. We have the base peak as well as the molecular ion peak. These 2 are really important. The molecular ion peak, which is typically the peak that is the furthest, that represents the molecular mass of the compound. And then the base peak represents the peak that has the highest intensity. So that's going to be at 100 always. And that represents the fragment that is occurring the most. Whenever you're being like given questions, you want to be actually looking at what kind of fragment is being produced that causes the space peak, and you want to write down that fragment in your answer. And then also say that the molecular ion peak represents the molecular mass, and therefore this is the molecular mass of the compound. So that's how you deduce it. All right, in terms of Mod 8 questions, it's really just about interpreting graphs. So it's really just about how many you can do and how many you expose yourself to. All right, I think I have this question put into my Slido. Let me check. Otherwise, we will move on. I think I do. Let me go check my Slido. Hopefully it's showing up on Slido. All right, so you're given the CNMR and you're given the infrared. So from here, try your best to determine the structure of the compound. And also, you're given a formula of C3H6O. Um, so yeah, I'll just like go back to the slide as well. It's the formula over here. So it's C3H6O. You just need to figure out the structure of it. Tetramethyl. Oh, okay, so the TMS peak typically only shows up in the HNMR. And no, it won't be the structure of that compound. You typically won't be able to ask to determine the structure of TMS, by the way. Most people are saying propanone. I'll just let you guys put in your responses. Propanol, someone's saying propanol. I'm getting my data sheet up on my phone as well, so I could explain the question. Okay, I think most people are writing propanone. Let me just let anyone who's writing their responses finish off. Someone has a new response, propanone. Okay, cool. Well, most people are writing propanone, and you guys are correct. Let me just close down the poll. Give me a second. All right, let's go back. So the structure, I mean, not structure, sorry, the formula has already been given to you. So it has a formula of C3H6O. You should be really looking at what compounds it could potentially be based on how many oxygens it has. In this case, it could really just be an aldehyde, a ketone, or even an alcohol. So if it were to be an alcohol, you would typically see like a broad peak. I think approximately in my data sheet, it says around 3,200-ish. So somewhere here, you should be seeing a broad peak. I'm not seeing that, so I already know it's not an alcohol. So that's pretty much useless. You can also see a really like sharp peak here at approximately 1,700. If you see this peak, this immediately indicates that there's a C double O bond. So you know it's a C double O bond, it's either going to be an aldehyde or a ketone, right? And then if we need to figure out which one it's going to be, really it could be either one in this case, because if you look at the CNMR over here, you can see here that there's a peak at approximately 210. And the compound, also you have two different environments here, so therefore it actually can't be an aldehyde, and I'll explain why. In this case, it's two environments, so two carbon environments. These two are identically the same, and therefore it's a C double O. If it were to be an aldehyde, so propanol, you would have a C double O and then a CH2 and then a CH3. And therefore you have three environments, so that can't happen. So therefore it has to be propanone. So for anyone who wrote propanol, that's not right. And then I think that was it. Most of the people wrote propanone anyways. So that's how you kind of deduce the compounds. All right, this one's a bit of a meaty question. So this question is asking you to determine the structure based on different kinds of spectrums that you have. Let me put up the question. I don't know if you guys will be able to see everything. It's really tiny. So you just need to determine the structure. So maybe what I'll do is I'll put it on the slideshow so you guys can see it a bit more clearly. And then you can just write down your answer on the slider. Someone wrote 2-methyl-propanoic acid. And then someone wrote 2-pentanone. Okay. Let's see if anyone else is putting their responses in. I'm just gonna see if 2-pentanone works, because I'm not exactly sure. Someone wrote propanoic acid. Okay, you're very close, by the way, whoever wrote. Someone wrote a really large, I think, amino acid. I honestly don't know what the hell that is. Maybe it's a protein. Would never ask you something that complex. Okay, I think most people seem to be done. And someone just wrote about infrared spectroscopy. You don't need to write that. They're just asking you the structure. They're not asking you how infrared works. So, yeah. I don't know if that was a joke. Okay. Let's look at the answers. So let me go back to the slide. All right. So for whoever wrote 2-pentanone, it can't be a ketone because we have this like peak. I like to call it a hairy beard because that just tells you that there's an OH acid group. And you can see it kind of is like very ragged, I guess. And also you have a C double O. So therefore, C double O plus OH acid is um, propanoic, like not propanoic acid, any kind of acid. So it can't be 2-pentanone. And then there's really just differences between like propanoic acid, 2-butanoic acid, and then like 2-methylpropanoic acid. So the reason why it can't be propanoic acid is because of the fact that we do actually have a methyl group. So really, this is the structure you should be getting. If we did have propanoic acid, then that means the molar mass is going to be smaller than what is being seen here, right? In terms of the rest, I think someone wrote butanoic acid. You have the same uh, problem over here. So yeah. And also like if it's an isomer, you got to make sure that it matches the HNMR and the CNMR spectrums as well. So always make sure that you try your answer, like trial it in the sense that it matches these spectrums. If it doesn't match the spectrum, then it's not going to be that compound. In terms of why it's this compound, we can see that it has an OH acid group and C double O bond, as you can see here. And then if we look at the HNMR and CNMR, we have 1, 2, 3 carbons within the carbon chain. And we only have 3 hydrogen environments because this is one environment, this is another environment, and these two are identical. Same thing for carbon environments. This is one environment, this is one environment, and then these two are identical. So just make sure you're aware of that. That's why you have 3 and 3 on this side. So that's how the splitting really occurs. And then for the OH, you have a singlet over here. And then for the CH group, you have a carbon that has 3 hydrogens. Therefore, by n+1, you'll be seeing a quartet. I know it's kind of hard to decipher. And then for the CH3, you have a carbon that's attached to only 1 hydrogen. So therefore, you'll be seeing a doublet. It's kind of hard to see, but there's actually a doublet there. So maybe if I could zoom in more, you'd be able to understand the HNMR spectrums. But yeah, that is really pretty much it in terms of Module 8. I know we didn't have time to go back and look at the Mod 6 questions, so I'll just scroll through and see which question seems relatively okay, and then go through it together. Let me pop one on Slido. All right, I think, no, not this one. Okay, I'll pop this question on Slido and you guys can have a go. This is Mod 6, by the way, just quickly revising over, and then I will answer all of your questions. Someone got 12.4. Let me check if that's correct. Where is the solutions? 1.3. Okay. Most people are getting the 12 point something range. I'll just wait for anyone else who wants to put in their response. Some people are getting 12.7. I'll just wait if anyone else wants to put in their responses. Okay. Most people are getting 12.4 or 12.7. I don't know if there's anything wrong in my solutions now. Just to tell what I got 12.4 as well. So let me close the poll and then we'll go through the solutions together. All right. Okay. All right. In terms of the question itself, it's asking you to find the final pH. So therefore, you need to determine limiting reagent for these kinds of questions. You have HCl reacting with NaOH, that goes to NaClAq plus H2O liquid. Find the number of moles of HCl and NaOH first. So you should be getting 0.0875 moles for HCl and then 0.1125 moles for NaOH. So therefore, you know that NaOH is an excess. Find the amount of excess that you have. So therefore, you should be getting 0.025, and that's the number of moles of OH minus. Because when NaOH dissociates, it goes to Na plus and then OH minus, and that's in 1-to-1 mole ratio. So that's why these two are the same. And therefore, you find POH, which you should be getting around 1.6, and then therefore pH should be approximately 12.4 to 2 decimal places. Remember, for pH, the lowest number of thick figs is the lowest number of decimal places that you'll be using. In this case, it's 2, so therefore I write it to 2 decimal places. So hopefully that helps. All right. I think we'll just move on to Q&A. And you guys can continue to put whatever questions you want in there, and I'm more than happy to answer them. All right, let's move on. So someone's asking, what values of KSP is it safe to assume that the small change assumption can be applied? I think I mentioned this earlier. So it's any value that's less than 10 to the power of -3. So if it's like 10 to the power of -4, -5, -6. It's really small. So you can just apply the small change assumption. Let me take that off. Okay. Someone asked, what raw mark estimate would I need to get 90 in the HSC? There's actually a way you can determine this. I was looking at that question whilst you guys were doing the question. And if you go to, I think there's like a HSC raw marks database on the internet. And I think I was looking at a value, approximately a raw mark of 81 in the exam in I think 2019. Sorry, a raw mark of 82 in 2019 gave you a aligned mark of 91. Assuming that the HSC is gonna get harder, you might just need like an 80-ish to get a mark of 90 in the HSC. But that being said, don't try to aim it in that sense. Try to maximize your marks as much as you can, because you don't know like if you're gonna stuff up a question, right? Like a question that you thought that you might get right might actually be the question that you get wrong at the end of the day. So just be careful of that. All right. Let me clear that question. To the person who asked about the last step of that one question, I have noted it down, so I will get back to you. All right, let me clear this. Okay. Someone asked, I'll get to why do aldehydes have a lower boiling point than ketones. It's simply just because that the ketone is surrounded by the other carbon, so that just makes it having a higher boiling point. But I'll explain a bit more about that later. Um, Someone asked, "Do you have the solution to the practice roadmap?" I don't think I do because I mainly put it as just an example, really, as to how a question could look like. So no, I don't. Sorry. And I think also someone asked, where do we find the solutions? There was a question somewhere. Like this entire like slide will be given like I think at the bottom of your page, I believe. So just check that out. Someone asked what is the best way to memorize cations and anions? Hmm. I think you're just better off doing a flowchart. I think there are also flowcharts um on the internet themselves. So you can just get one of them and then just um like memorize that. Someone, let me clear that question again. Okay. Someone asked, since I was also quite interested in biotech, I was wondering how you find your course so far and what it's like. Thank you. I'm really like not into like a biotechy subjects yet because for first year it's always just like foundational sciences. So I'm really just covering like the basics, like the basics of chemistry and like human anatomy and things like that. So yeah, I don't know how it's gonna be like yet so far. Because I've looked at my subject outline and I really have the biotechy courses mainly in like third year or fourth year. So yeah, first year is just like all the foundational stuff. Unfortunately, it's not really. I mean, it's interesting, but it's like not that uh like detailed so far. Uh, Also, someone asked if I have solutions for the spare questions. I don't think I do, unfortunately. Um, if you guys do have questions, just like cross check with your peers. I only included them in case like if we didn't have enough time, then we could just add more. But I think we have like really exhausted our time. So yeah, okay. Someone asked for the last question. Don't we need to convert the NaOH as a concentration? Oh, wait a sec. Wait a sec. Maybe that's why. I think someone pointed out my mistake. Let's go back. Where is it? Where is that question? Yeah, so whoever pointed that out, you are correct. I completely forgot that step, didn't I? Okay, that probably explains why a lot of people are getting 12.7 and I'm getting 12.4. You would need to divide it by the total volume, so therefore it's just pretty much 350 plus 150 in liters, right? So I think in that case 12.7 seems like a more correct value. So you are right. Whenever you're doing POH or pH, convert it into concentration. And I'm sorry for that mistake. Thank you for pointing it out. All right. Someone asked, does this relate to Mode, but ideally, what complexations reactions do we need to memorize besides the AGCL? Uh-huh. Yeah, so like complexation is a very niche topic in HSC. I think I memorized the same one as you did. So just have like one like case study at the back of your mind. Um, but other than that, you wouldn't really need to memorize anything else. So yeah. Okay, let me clear that question. Give me 1 second. Okay, yeah, for the person who talked about the pH, you're right. It's not number of moles, it's concentration. For the person who asked, by the why do aldehydes have a lower boiling point? I think I kind of explained it. It's a bit out of the scope, but really it's just because of the fact that ketones are surrounded by those carbons and they contribute to an increase in boiling point. A bit of it relates to like the electrons, like being shared and like and all that. So that's kind of a bit beyond the scope. Is it okay to write one pentanol as pentanol? Yes, technically yes, but it's just easy to write pentanol, right? Because then if you have like other like substituents, it just makes it more nicer. I've been used to writing it as pentanol, so I have that personal bias. But I think one pentanol is also IUPAC nomenclature. Just do what your school taught you. I think that's probably the safest option that we have. My school taught me to write it as pentanol. Someone asked, can you please do an example of answering questions to sig fig? Yes. So I've already mentioned about the decimal place thing. So if we just like go back to one of the questions that we did. Okay, this is also a pH question. Okay, so for like these kinds of questions, if they just give you like a value, then let's just say one value, then you round it off to the sig fig of that value. So in this case, it's 1. So therefore, you round it up to 1 sig fig. If, let's say, we go to a question where there's multiple sig figs, let me get one up. Does this have different numbers? No, it doesn't. All right, let me get a question up and hopefully that should explain some things. Okay, for a question like this, let's say, if you have like multiple values, then you want to look at which number has the lowest number of sig figs. In this case, all of them are 4, so you round it up to 4 sig figs. Yeah, and this is also like the same thing, different numbers, but all of them are 4 sig figs, so therefore 4 sig figs. Whereas in a question like this, you have like 2 sig figs, you have 3 sig figs, so therefore you stick with 2. Hopefully that answers your question. Someone asked about the Aboriginal acid base thing. Yes, I think I know what you're talking about. It's like, I think it's like the stuff about like clay, where like clay was like swallowed to help with like, I don't know, like indigestion or something. I think I still remember that dot point. You would, yes, need to know a bit about it. I think like the clay example is one thing. There's also a plant called pig face. If you Google it, and that was I think a plant that was used for stings, like within like aquatic life, and I think it has like a compound that helps to act as a base. But the clay one is a main example. So yes, you would need to know at least like a case study for that. And there's also one for equilibrium. I think there is. I think you're talking about the cycad plant. So there is, I think the cycad plant contains cycasin, and that's the plant, like cycasin can be dissolved in water and it can be leached out. So that one's relating to how like you can use solubility, right? So that's one study. And then the acid base one is like the clay example that I gave you. I don't remember what exactly the clay was. I think it was, actually, no, I really don't remember. So just Google what exactly the clay is and make sure you know how to write down the dissociation equation of that, as well as to how it reacts with an acid or a base. All right, let me clear that question. Can you please explain ice tables and how they work? Yes, so let me get up an ice table solution. So, okay, ice tables are really nice to represent changes in equilibrium. So there are, I guess, 3 rows you could say. So you have initial, represented by I, change, represented by C, E, representing equilibrium. And in ice table, you write down the numbers as concentrations, right? And the kinds of species that you have within an ice table are the ones that are either aqueous or gaseous. You don't include liquids or solids. So yeah, in this case, I've included magnesium and carbonate because both of them are aqueous, and those are the ones that change in concentration. And as it suggests, you pretty much write down the initial values of both of them that you have, the change. So the change is represented by x, and like I said earlier, if you want to define x, you could say that, let x be the change in concentration of Mg2 plus. So therefore, when it shifts right, this equilibrium, and dissociates, you have plus x, and then you have plus x for carbonate as well, because both of them are in 1-to-1 molar ratios. And then finally, you just add up whatever you have in initial and change to represent what is in equilibrium. Here I have 0 plus x, therefore that's just x, and then 0.001 plus x, so therefore it's just that within equilibrium. So that's how you write it out. And whatever values that you're getting here in equilibrium, you can just plug them in into the KEQ expressions. So that's why we use ice tables. It's just a nice way to structure your responses. And it doesn't make you confused, because I find that if I do questions without ice tables, I get confused as well. So it's just better if you use them. Hopefully that helps. Sorry, when do we use decimal places and sig figs again? So for pH, it's decimal, and then for others, it's just sig figs. For point of difference, would we get marked down for doing the larger number? So if you do the one that has a smaller sum, but it has a larger difference, then yes, you get marked down. Overall, and yes, you pretty much get marked down if you use a larger number when there's another option available. What's your best advice for answering questions relating to conducting investigations for a certain area, for example, indicators? I think there was a dot point on this. Could you please elaborate? Because I think I forgot what the dot point was. Are you talking about like buffers as well? Like, for example, demonstrating how a buffer works. If you're talking about like conducting investigations in general, you should be writing down a method. So number it and then like add like numerical values to represent it and like write it down from there, if that makes sense. Another person asked where would be able to find this PowerPoint. I think I mentioned this. So it should be at the bottom of your screen. So I think there would be a resources section and you should be able to find it there. So hopefully that helps. Okay, someone asked, why is MgCO3 not in the expression? So if we go back, that's because MgCO3 is a solid, right? And solids don't have a variable concentration. Same thing for like the stuff with water. So if I go back, yeah, so water is a liquid, so therefore it's not going to have a variable concentration. Anything that doesn't have a variable concentration, we do not include within the KEQ expression. So hopefully that answers your question. I think someone also asked, what are buffer regions in titration graphs? Good question. Do I have an example of a titration graph? No, I do not. So whenever you have like a weak acid or a weak base within a titration graph, that just represents how the weak acid or weak base dissociates. And because it's dissociating, remember how buffers are pretty much just a weak acid or weak base and its conjugate base or weak acid at similar concentrations. When it's dissociating and that dissociation happens so that they're both at similar concentration, then you have a buffer region happening. And buffers pretty much resist changes to pH. So you're not really going to see a change in pH within that graph. So if you see a point in the graph where the pH is not really increasing, then you know it's a buffer region. And then you have to identify which of it's going to be. So like what kind of species? Is it an acid, like a weak acid, or a weak base? And that's dependent upon the species that's within the graph itself. So yeah. All right, I think that's pretty much the end of this question, really. I do have one final question for you guys. Let me put that up. Did you guys enjoy today's lecture? And hopefully, did you find it useful? Okay, I'm so glad that you guys did find it useful. Um, but yeah, if there's really no other questions, then I think I'll let you guys head off for lunch. And good luck with the rest of your HSC. Thank you for attending. Bye.